Good morning, everyone. I am Sinha. I am going to present my work titled as Probing Jet Emission in the Extreme Blazar TX0210 plus 515 through MAGIC and AstroSat observation under supervision of Dr. Ridhavan Chatterjee. Let's begin. Here is the outline of my talk. First, I will introduce Blazars. Then I will talk about the source TX0210 plus 515, which I have studied, and then the observational facilities used, then the data analysis, followed by the variability and timeline analysis of the source. After that, the broadband ACD modeling, and then finally the results. So blazars are a type of active galactic nuclei whose relativistic bipolar jets are aligned towards us. They are extremely bright and emit across the entire electromagnetic spectrum, ranging from radio to teraelectron-volt gamma rays. Their emission is extremely variable and mostly non-thermal. To characterize their emission, the energy output of a blazar is plotted against the frequency or the energy, which is called the spectral energy distribution or ACD. For a typical blazar ACD, it looks somewhat a double hump shape, where the first peak corresponds to the synchrotron peak, and it is located around the infrared and X-ray band, and the second peak or the high energy peak is located around the gamma ray energies. Now, what powers this extreme emission? For that, I have studied the source TXA0210 plus 515, which is a newly discovered TAV emitter. It is a faint source, but it has some extreme spectral properties, such as its synchrotron peak or the first peak in the ACD lies beyond the 1 keV mark in the X-ray. And the second peak in the ACD is located around the 1 keV mark. Due to these extreme properties, it is categorized as extreme high frequency peak BL Lac or EHBL. To study the source, we have used various observational facilities across different wavebands, starting from optical, the Growth India telescope. For UV optical, we use the SWIFT UVOT data, and for X-ray band, we use indigenous AstroSat, and high energy gamma ray band, the Fermi-LAT, and for very high energy gamma ray band, we use the MAGIC telescope data, which is located in Spain. These are the X-ray spectrum for the MAGIC and Fermi-LAT telescope. The MAGIC data is taken between 2015 to 2017, and these were the published data in the SCRE et al. And in the right hand, the Fermi-LAT data taken between 2015 to 2023. The Fermi-LAT data is fitted with a simple power law model and corrected for the EHBL absorption using the 2021 Saldana-Lopez model. For X-ray band, we have used the AstroSat data. We all know that AstroSat, India's first multi-wavelength space-based telescope, launched in 2015 by the Indian Space Research Organization, or ISRO. It has 5 detectors: UV for far UV and optical imaging, SXT for soft X-ray band, LACPC for hard X-ray, and CZTI for the very hard X-rays, and SSM, which monitors the X-ray transients. For our study, we used the LACPC and SXT data, which was collected during July and September of 2022. These are the X-ray spectrum for the 2 epochs in July and September. These 2 data were fitted with the log parabola model with galactic absorption. And in the red, the LACPC data is shown, and in blue, the SXT data. Both the data were corrected for galactic absorption. These are the fitting parameters. Here we also shown the power law model, and for fitting these 2 spectra, we have fixed the galactic absorption value to 0.146 found in the literature. And these are the X-ray light curve of the source. in the left panel, the observation 1, and in the right, the observation 2 is shown. We can see the observation 2 is a high flux state. That means the source is in a more active state in the observational period compared to observation 1. So we calculated the variability time scale for the observation 2 for the SXT data. We calculated the variability time scale to be 6 hours, and what this variability can tell us. So short variability time scale implies a compact emission region. Using this formula, we constrain the emitting region upper limit to be 1.3 into 10 to the power 16 centimeter. Here we have used the Doppler factor 20 and redshift of 0.049. Now we did the time lag analysis of the same light curve. We divided the light curve in two energy bands, soft X-ray and hard X-ray. Soft X-ray is ranging from 0.5 to 1.5 keV, and the hard X-ray is 1.5 to 5.5 keV. These two light curves look somewhat correlated, so we did a cross-correlation analysis and found a time lag of nearly 5 hours. And with this time lag, we estimated the jet magnetic field to be 0.08 Gauss, and for the same Doppler factor and redshift. Now we model the broadband ACD with the one-zone leptonic model. In this model, the first peak or the synchrotron peak is assumed to be originated by the relativistic electrons spiraling in the jet's magnetic field, which emits synchrotron radiation. And the high energy peak or the inverse Compton peak is originated by the high energy photons, which are produced in the inverse Compton scattering of low energy photons to the same population of electrons responsible for the synchrotron peak. And here, the one zone stands for the single spherical region from where the emission is emitted, and the leptonic because only the leptons or the electrons are responsible for this process, and SSC because the synchrotron self-Compton or the low energy photon here, the same photons emitted in the synchrotron emission. For the ACD modeling, we use the public available jet set code and electron distribution. We choose the broken power law. In the code, and the thermal emission from the host galaxy is modeled using a 13 gigayear host galaxy template from SWAT database. More details can be found in this paper. This is the broadband ACD for the AstroSat observation 1. Here the gray markers are the archival data from SSBC archive, and in the TeV range, the blue markers are the Fermi-LAT data, and in extreme right, the purple are the MAGIC data, and in middle, in the X-ray band, the SXT and LAC data is shown, and in optical, the UVOT and the growth India data is shown. In the right, these are the fitting parameters. We got a very low magnetic field, and the emission region is well below the 1.3 into 10 to the 16 mark, which is consistent, and the synchrotron peak is nearly about 2.87 into 10 to the 17 hertz, and inverse Compton peak is nearly 1 TeV, but below the 1 TeV mark. This is the observation 2. As I previously mentioned, the observation 2 is in a high flux state, so its parameter, the magnetic field and the emission region size is also higher than the previous one, and the synchrotron peak and the inverse Compton peak is also higher. Here are the summary of key results. We found that the magnetic field of the jet is very low, 0.01 to 0.3 Gauss, and the emission region is very compact, and the Doppler factor is very high than usual blazars, 30 to 48. And the synchrotron peak and IC peak are both higher in the case of the observation 2. There is some conclusion. The source is a EHBL source, and it is a compact source, and it is an efficient particle accelerator because it accelerates photons up to the TeV energies, and the multi-wavelength variability studies and the spectral shape of the ACD are consistent with the ones of synchrotron self-Compton model. And we can also see the harder and brighter trend is evident from these two observations. And this kind of blazars are important to study the cosmic ray and neutrino detection. So we need further study for this. And at last, I would like to acknowledge my supervisor and seniors for their contribution to this work. Thank you.
Thank you so much. That was a wonderful talk. Questions?
I just have a quick clarification. For the growth in their data,
yes,
was it also involved in the, you said Professor Pratik Majumdar was the PI, was it like
no.
simultaneous observation?
No.
That is archival data or what?
No, growth data is simultaneous to only observation 1. And the MAGIC data and the Fermi-LAT data was quasi-simultaneous because the detection is very low for them. And we averaged from 2015 to 2022 in the high energy gamma ray band. And the X-ray data is 7-day data for in a gap of 1 month.
Just one or two clarifications. I missed something that you did. The magnetic field.
Yes.
There are first observation it came to the point 0.08
yes,
or
yes.
something. And
yes.
Next one 0.01.
No, next one is higher.
Oh, I missed it.
Yes.
And other thing is, can you go to your chart or go to the slide? I mean, what Pratik did, Pratik, you got the data from Pratik?
Yes. Pratik sir was PI of this AstroSat observation. Yes, data.
No. You go to the initial plot. It's maybe I think the second or third where you have made a normal distribution, not normal log parabola.
Yes, this one.
Log parabola. Yeah, that one.
Yeah. Yes, I mean, but then the chi-square theta I have seen is marvelous. I mean, chi-square for degrees of freedom is almost equal to 1.
Nearly.
But why it is called this what you call log parabola distribution?
Because
log I understand now, actually, because you are talking in logs. Parabola, just a passing question. It's not related to this.
No, it looks like a parabolic in the log plot, so that is called typical blazar spectrum. Most of them are log parabolic. Fitted is the best fit. It is assumed in the literature, so we have used.
Alpha has a value 2 also.
That alpha is square, e square. This no, the other thing is that that you plotted these data points, and then
yes,
fitted with
yes.
Data points. The 4-5 data points you have extracted from a histogram where the amount of data are there, and then you make it a histogram distribution, and from that you picked up that point and another one.
No. We
just data.
Fitted results. This is.
How do you extract the counts? That's the question.
Those counts, those discrete points and those error bars that you have.
No. I didn't use any histogram. I extracted the data and just plotted and fitted the spectrum.
Extracted the data, but at certain energy, there is 1 point, right?
Yes. Yes, the software did this inherently. I didn't. Yes. Yes. Detection.
And then from there, pick out that point and
yes.
error investigate and put it. Like
yes.
This is like, I mean, ice cube data they publish in that way. So it is the same thing, right?
Yes.
So, but you, I mean, you took those discrete points from your whatever.
Raw data.
Yeah. So, yeah, that means
yes.
then you have figured it out. That's it.
Okay. We can have, I think, one more question from the audience. Question. Thank you so much. Then let's thank the speaker.